All right. So welcome to lecture number 9. And as you can see from today's topic, we will leave the multi-body dynamics for good. So we are not revisiting that topic we are not going to do it any longer. So from this on, we're going to look at the different subject matters. And the first thing what I would like to do is that I would like you to give or learn the basics about modeling of hydraulic systems. And that takes roughly, what I would say, 2.5 weeks. So it's going to be this week. So is that a thumb up?
Yes.
Okay, thank you. So it's really so dark, that I cannot see you guys very well. So even our communication today will be difficult. Maybe I can just hardly see if you do this. Hardly. All right. Anyway, so 2.5 weeks is about hydraulics. Today we will get started, and then we will follow up on next Tuesday, if I remember correctly. So the next week we are back on Tuesday. So the lecture will be on Tuesday, and I think it is not going to be this lecture room, but someplace else. I need to check that. But anyways, and then we need a little bit of time from lecture ID 11 to wrap up the topic of hydraulics. And this hydraulic modeling is actually the really main body of material in this second period. Maybe is someone in the back, maybe is it possible to close the door because there is a little bit of traffic in the corridor? Okay, thank you. So today we will get started with the hydraulics. But prior to that, I have an announcement to make. There is a university spin-off that is the company that is called MEVEA. The MEVEA is the one that is located in a business park that is next to university. So physically is, what it is, 100 meters away from us, 200 meters away from us. So it's very nearby. And that's a company that is specialized to multi-body system dynamics. So they are actually doing the business out of the theoretical studies that we are learning in this course. And they have a particular feature in their products that makes them as a unique company in the worldwide. And that's the fact that they can solve things in real time. That, by the way, is a topic that I will get back later in this period. And I would like you to understand the basics about the real-time simulation and gamification concepts. But this company is looking for more manpower, female power, whatever. They just need more power. And they are offering intern positions. Don't know the details, what exactly they're offering, but I recommend you to visit in their website, which is mevea.com, and take a look. Put your contact information to that website and to see what exactly they can offer to you. And they insist, or they didn't insist, but they said that it would be nice if I can play a couple videos about their business for you guys. I'll make a little bit of marketing work. So do you mind if we take a look? Yes, you mind. You don't. So can I play those videos? All right, so the first video is about the MEVEA seminar that was more than a month ago in Helsinki region. And some of you participated, and those of you that did not participate, that's how it was. So this tells a little bit about how many people they were able to attract to that meeting even. Why is it the music is not coming from the loudspeakers? Anyways. Is this the risky business? Anyways. Can you hear the music? Barely. Okay, there's another video too, but that I'm gonna skip because that's a bit too commercial in my mind. It tells, well, there is Daycaster, which is a leaper, big company that is speaking very highly about MEVEA performance. So I think they speak a bit too highly to be realistic. But anyway, so my message to you is that they're looking for more people that they can work with. And that, the one possibility is that you just contact the MEVEA and ask what exactly they can offer. Also, it's good to know that my research team is cooperating very closely with MEVEA. So that's another way that you can find your way to MEVEA, and not just the MEVEA, but other bigger companies in Finnish industry, because MEVEA's customers are typically those big production companies in Finland. So the ones that are like not the gigantic in a size, but in a Finnish scale they are big. So if your dream is to work in Finnish industry, this could be your opportunity to do so. Okay, so that's that commercial break, and now we're gonna go back to real deal, and the real deal is hydraulics. And again, I would like you to take a look at this picture, because this picture is serving as a guideline for this course. And like I mentioned earlier, so far we've been discussing about the mechanical components only. Next, I would like to introduce you the model of hydraulic actuators. And you know that the hydraulic actuators are not the only kind of actuators you can find. There are many different kinds of actuators. Important thing when you look at this figure is to understand that actuators and the mechanical components are coupled together. And because they are coupled together, they are assembled together in a real product, it makes no sense to analyze just the mechanical structure. Because I've been seeing millions of studies that there is a very detailed description of mechanical structure, and then when you're asking, what about the actuators? Well, the response is that we are guessing the forces that the actuators are producing. Guessing the forces, how much the actuators are producing. So this is roughly speaking, this is rough speak, but if you have like this kind of simple crane, which is a lift arm only, that is actuated by hydraulics, roughly speaking, the situation is such that you have an equation which is externally applied forces equal than inertial forces. And what are these externally applied forces that is actuating the system? Well, this one here is coming from the hydraulics. And what is that you're doing with this equation? You're solving the acceleration, but think, what's the consequences if you're guessing how much force is produced by hydraulics? So you're guessing this guy. So what's the value of solving acceleration? No value. So that makes no sense. Another way around, sometimes you hear these very sophisticated stories like how there is super detailed model about the hydraulics or other actuators, and then you ask, okay, what about the overall performance? And the response is that I have no idea. I would like you to have that idea. I would like you to understand that the simulation model is supposed to be a close representation of real machine. And the real machine is a assembled entity where you can find components associated to mechanical structure and components associated to actuators. And they are coupled together. So they need to be solved simultaneously. Now, what are the other means of actuators you can find out there? Well, of course, you know that there's a big trend to replace hydraulic actuators by electric drives. And this is actually what happens out there. So it is a trend that happens, and there's good examples where hydraulic actuators are replaced by electric drives, but typically those cases and examples you can find in industrial applications, like paper making machines and other big machines that are in industrial environment. Mobile machine, that trend is also there, but it's more difficult to do that in mobile machines. That's simply because the power density in hydraulics is really good. So it's a possible to build something that is very small in a physical size, yet able to produce significant amount of forces. And that you can do with the hydraulics. Of course, there could be also pneumatic drives. Pneumatic drives are not often used because that the pneumatics here is very flexible. That makes it challenging to use that in a server application where there is a feedback. So the controlling of pneumatic actuators is a challenge. It's possible, but it's not as easy as, say, hydraulics. And then there's a bunch of more exotic actuators like water hydraulics that was very much in fashion a few years back, maybe more than 10 years back, but is not in fashion anymore. It comes with certain difficulties. And one of the difficulties associated with water hydraulics is that it requires quite exotic material selections and materials that are used in a water hydraulic components. And that's simply because the water is not the good lubricant. Even though that there is this phrase which says water is the oldest lubricant, it may be, but it's still not very good lubricant. And because it's not very good lubricant, you need to use exotic material like ceramics to build the components that are used in water hydraulics. Also, it says that the good thing about the water hydraulics is that it can be considered to be environmentally healthy. And yes, it is. If you just use water, so water is not dangerous in any means. But the problem associated with water is that what I have in my cup here is a water. If I leave my cup of water to be in this table for the next 6 months, there's not going to be water anymore, but it's going to be green thing, and it's going to go, monster will come out from my cup. And that's the feature of the water. So how is it we can kill those monsters? Well, we can put a little bit of poison on it, and we can get rid of that. But that's about the environmentally healthy approach. So still comes with certain difficulties. But of course, it's if I think about the pneumatics, electric drives, water hydraulics, I guess that really the one that is very much and will change the life quite a bit is electric drives. Then, of course, there is a bunch of really exotic actuators like piezoelectronics, memory materials, and so on and so forth. For sure, we are not going to touch that topic, but that's, again, for your information, that actuators are coupled to mechanics. Then, again, when we look at the big picture of this course, we're going to touch a little bit about how to do this control system. And really, my favorite part of the course will be lecture ID 12, the last lecture. That's about this gamification, real-time simulation, and that tells you how the user can be accounted. We are not going to touch too much about the environment models, which is a working process, but there is an outstanding course that will start on, in January, beginning of January. That's period number 3. That course is entitled as a simulation laboratory course, and it is outstanding course. So if you make a list of the best courses in this university, first comes is that laboratory course, then comes nothing, and then when you go down in a line, then the others come slowly, but that's like clearly the best. It is. I would like you to consider to participate. I will be, by the way, lecturing that course, but that's not related to that what it is the best course. It is simply that the subject matter is very exciting. It's about real-time simulation. We're going to learn to use the MEVEA simulators in different applications. It's going to be a lot of fun. Please consider. And it's not theoretically challenging. Really, this course is theoretically painful, very painful, because we need to learn the basics. But once we learn the basics, then the follow-up course, which is that laboratory course, is all about sun shining and warm weather, so it's pleasant. So we are applying those theoretical knowledge to practical problems. So that's why it is pleasant course. Okay, so let's look at the examples of different models where the hydraulics is used. Any comments, by the way, regarding the actuators? No? Makes sense. Okay, what about any comments regarding the MEVEA internship position? Are you planning to apply? We'll see, too early to say. I cannot really see your faces, so you can have any face you want. Okay, so a few examples where the hydraulics is used. So, of course, like I mentioned, is heavily used in the application of mobile machines, and that's simply because the power density is very good. So here's an example about harvester crane. It's not very recent model. I believe this model is maybe say 15, 20 years old, and it is made by using a commercial software Adams, and it's just solving the motion of the crane such the way that is actuated by hydraulics. But again, typical example where the hydraulics is used, because in the mobile application you want to have a small physical dimension and you want to produce a significant amount of forces. Then this is an industrial application, which is deflection compensated roll. It's all about combination of hydraulics and mechanics. I need to explain a little bit what exactly is this thing, but this is one type of the roll that is used in a paper making process, and it consists of two main components. The one that is shaft, that is standing still, so it's not rotating. The shaft, let me see if I'm able to draw. So is this component, this, I don't know, what color is this? Purple, like a little bit of purple, red kind of color, that's the one that is standing still. And then there's a shell, which is actually the moving component of deflection compensated roll. So it's going to be this component here. And these two main bodies are connected together with hydraulics. So there are loading shoes that are the ones that you can barely see. So those are the ones that you can see here. Let me take my drawings off. Well, here you can see a little bit how it is. So they're pretty much like a shoe like this. And it will be actuated such the way that the pressure will be pressed to this side, and there is a drilling that goes through that sole, this shoe, and then because of that drilling there will be a thin layer of oil that is separating the loading shoe and the cell. Well, so this system acts like a zonal bearing, so it's a bearing system, but it's a very special bearing system because it also introducing forces to that cell structure, which is blue in the color. And why it is introducing those forces? Because in this particular component, you wanted to compensate the deflection due to the gravity, like the name implies. So how it goes? It goes such the way that okay, so there is this shaft that is standing still, and then this cell, because of the gravity, it will be bended. You know, that's what's going to happen. And then because you have these loading shoes, you can introduce the forces such the way that they can go like pretty much like you want. Like this is an example. Now it's possible to keep this line here, this line that is pressed against another roll, to be completely straight. And not just completely straight, but you know, making a profiling, something that is based on the need of production. So it's all about hydraulics and mechanics. Then how is that you can model the hydraulics? And you know, this is an example that it is a movie from MEVEA software. So this is a crane that is spraying a concrete to tunnels. And soon you will see how the hydraulic circuit look like. It's gonna come after this. So this is how the hydraulic circuit look like. Again, is an automated user interface that allows you to introduce those components to screen and connect these components with the hoses like they are connected in reality. But again, I'm going to explain what happens behind the scheme. I would like you to understand what's the theory that is used to compute the hydraulics. Because again, it's important to know what exactly happens to make sure that you're using the method the way that it is designed to be used. So that's why these 2.5 lectures about the hydraulics is not enough to just to put these signs to the screen, connect them with the hoses, and then, you know, to take a look. But you need to know what exactly happens under the hood. So that's what this lecture set is about. But you can see that this is a very nice animation. This is a feature of Mevea software that even the spool position is visualized. So typically it goes such the way that the user is controlling joystick. Joystick sends a signal to direction valve, and then there is a spool that is moving back and forth, controlling the flow and pressure, actually power, and then that motion is actually visualized in terms of motion of spool, like you just saw it. Okay, that's about the introduction. Happy? Okay, so let's move on. So let's go to real deal then. So let's take a, I need to go here. Okay, so let's get started from the hydraulic modeling. By the way, this is not going to be a rocky roll. This is going to be a pleasant story, particularly if comparing to some of the painful topics in multi-body dynamics. Concept of virtual work is an example. This is going to be very straightforward. So the mathematics you needed here is almost next to nothing. So you need to be able to summarize components together, subtract them with each other. That's pretty much it. So it's not going to be complicated mathematics. But it comes with another difficulties, which I'm going to introduce a bit later to you. Okay, so let's get started. And the first thing that I would like to explain here is the properties of fluids. And there are only two properties that are important in terms of modeling. And out of these two properties, actually the one only is really important. Another one is good to know. What is really important is a bulk modulus, by the way. And that's what I'm going to ask in my first in-class quiz. If you want, you can log into Socrates already this time. But I'm asking, what is a physical interpretation? Well, I don't remember exactly what was the question, but it's something like, what is a role of bulk modulus? What the bulk modulus is doing for you. And I can tell you that already. It is describing the flexibility. It's describing the flexibility of fluid. And that's, by the way, is very, very essential when we're looking at the dynamics of hydraulically driven structures. So another property that is less important is viscosity. Viscosity is less important because it actually only plays an important role in terms of laminar flow. That's a type of the flow that you don't know yet. But for your information, there are two types of flow. There's a turbulent flow and a laminar flow. A laminar flow is less common, particularly when we're looking at mobile applications, because it takes place when the pressure difference through the orifice is slow, and that's typically not the case in mobile machines. So those are the two features we're looking at, and we're going to get started from the bulk models. All right, so here's a little bit of same thing that I just explained to you. So two features we're going to look at. First one is bulk modulus, and then is a viscosity. They're mentioned in a different order here. And viscosity, like I already explained, it's important when you look at the laminar flow. But laminar flow is not common for us. It takes a place, like in case of that, this loading shoe we look at in that paper making, this roll that is used in a paper making process. Then the flow through that shoe is actually laminar flow. But other than that, it's not very common flow type. So then the bulk modulus, that's something that describes the flexibility of hydraulics. This, by the way, is super important to understand, that we have to describe the flexibility of fluid. And why is that? Because every now and then you hear these stories that you don't need to worry about the flexibility of fluid because it's so rigid that it's not affecting the response of your system. But it does. It actually makes a big difference. Because sometimes the major source of flexibility can be hydraulic actuators. It may sound a little bit surprising, but yes, it may be the case that the flexibility of system is not because of mechanical flexibility, but because of flexibility of fluid. You know that for sure the fluid is flexible, and I can tell you why. Because when I'm speaking to you, you hear me, right? Yes? So you hear me. Why is that you hear me? Because what happens in the physics? we are not going to go inside of my brain, but what happens after that is that there is a waves that is coming from me to your ear, and you hearing those waves. So the waves makes it possible to hear me. Well, I'm not speaking about understanding, but just hearing. Hearing, you hear me. Okay, that's because the waves are traveling in your ear, and it seems to be no problem. I mean, hearing-wise. Okay, what happens if we're gonna fill this place with water? Let's put this out. Let's get under the swimming pool, and then I'm speaking in a swimming pool. How that would be? No difference really. Then you're still gonna hear me like this. But now what comes really difficult is understanding. Really it comes difficult because it's no longer clear when I'm speaking. You don't hear me so clear anymore. Why is that? Because, why is that you're able to hear me in the first place? That's because, again, waves are traveling in the water. So that definitely is flexible, because if it would be rigid, there will be no way whatsoever that the waves can travel within that material. Okay, so we're going to take a look at the bulk models. So without further ado, let's get into that thing and let's look what is a bulk models. Very often this is something that I'm asking in a written exam. And again, first in class quiz about the bulk models. And I'm asking a physical interpretation, and it's a flexibility. You know where I'm aiming here? You see, it's called 100%. We'll see if it goes, if it really goes. But that would be outstanding. That would be outstanding start for the new subject matter, which is hydraulics. All right, so I have here unrealistic container, because this container is something you don't find in real life, but I don't care about that. So I have a container that is rigid. So there is no flexibility in this container whatsoever, no matter what you're gonna do with this container. So the container is the one that is here, green in color. So this one is a container, and the container is open in the top, and then I'm gonna have a lid. Now the lid is the one that is this one here. There's a lid is exactly the size that there's this open space of the container. And what I'm then doing here is that I'm pressing the lid inside of the container. And what I have inside of the container is a fluid. So I have here hydraulic fluid. Or well, it could be whatever you want, but let's say that there's a hydraulic oil that in this container. Now what will happen as a consequence of my force? Obviously, if the force is high, like coming from, my hand, so then there's quite a bit of force. So I'm able to press the lid inside of that fluid, right? I can do it. Of course, depending on the case, it needs significant amount of forces, but I'm able to press it inside. And because I'm able to press it inside, the volume here is actually changing. It is decreasing. The volume of the fluid is getting smaller, right? What else happens? Another thing that happens is that the pressure inside of the container increases. So volume decreases, pressure increases. You agree with me? Okay. This ratio, how is a ratio between pressure difference, volume difference? That's the definition of bulk models. That tells you how flexible is your hydraulics. That is flexible. You can always make this setup in real life and press the lid with the significant amount of forces. And yes, it's going to move downwards. And while it is moving downwards, the volume is getting smaller, pressure is getting bigger. Okay? Now, this setup hypothetically was something that the volume size was considered to be unit in a size. Well, to make this more general, let's consider the case in any size of container. So any size of container that we can get by dividing the change of the volume by volume size itself. That's make it possible to define the bulk model in such a way that is minus volume size and then the pressure difference and volume difference. That's what it is. Now in real life, the bulk modulus, which is a property of fluid, property of oil that is used in hydraulics, is actually, the bulk model is actually a function of number of different things. It is this picture is not clear at all, but let me tell you what I have in this picture. I have here x-axis, that is a temperature. It is so low quality that I'm having a hard time by myself to see what this says, what are the numbers. That doesn't matter, but what I have here in a y-axis is a bulk model, this one here. The bulk model is here in a y-axis, and then I have here different pressures, and how the different pressures is a function of temperature. And you can see that pressure affects the bulk models, because here the pressure is this is an atmospheric pressure. This is a 350 bar, which is typically maximum you can find in a mobile application. This is 1,000 bar, a little bit unrealistic number. So anyways, you can see that it's a function of pressure and it is a function of temperature. In a modeling, we don't care about that. We simply have so many different variables and so many different parameters, so it's becoming difficult to account all of them. And this is the one thing that we are not going to account in a real life modeling. But instead, we're going to just say that the bulk models, regardless of the temperature, regardless of the pressure inside of the fluid, will be a constant value. So it's having the constant value. And the good approximation that is very often used is 1,500 megapascal. So that's pretty much the value that is recommended you to use here. Now, it's somewhere, let me see again, it's here. This is the line that corresponds to that. And I think it is a good approximation. So it's good average from the values that is introduced here. So that's how it goes. Now, of course, these experiments we made in the beginning is not realistic, like I explained, because you can't really find something that is a rigid container. That's not from this planet. It's not just possible to do it, because regardless of always your container is always flexible. Like every single body here is a flexible body. Now, that's strictly speaking. Now, we need to expand this definition of bulk models a little bit. So we need to look at the bigger picture. We need to look at what are the features that, in addition to flexibility of fluid, will affect the flexibility of hydraulics. And we know that often there is an amount of dissolved air in the hydraulics, and air is 1,000 times, well, actually more than 1,000 times more flexible than oil. That, by the way, is the reason again why you hear me so well, and you will hear me so difficultly when we would be going under the water, because air is so flexible. And you can tell that when you take a pump that you use to put the pressure to your bicycle tires, you can close the one end of the pump and you can still move the piston back and forth. If you would fill the pump with the water or oil, it will be very hard to move the piston back and forth. You need a lot of power and a lot of force to make it happen. But now, there's always a certain amount of air that is dissolved in your hydraulic system, so we have to account that. And also we have to account the fact that the container is not rigid, but is flexible. If we speak about hydraulic cylinders made out of the steel material, flexibility is not very significant, but there are components where the flexibility is significant. An example is rubber hoses that is often used to connect the different components to each other. So rubber hoses will introduce significant amount of additional flexibility. So the question is, how is that we can extend the definition of bulk models to account all these factors that is affecting the flexibility? And we can make it happen by comparing something that is called effective bulk models. Effective bulk model stands to the fact that now everything will be accounted. How to make that happen? Let's take a look at another setup. Here in this setup, I have two containers that are connected together such the way that the connection itself allowing flow to travel back and forth without any pressure differences. So if I have a setup like this, it is likely that the pressure here will be the same that the pressure here if nothing significant happens here. Because, you know, here this throttle, this area here is big enough that it's not introducing any pressure losses. So I can consider this as a one container that is consisting of two parts. So what are the parts? So this is a volume 1 associated to this container, and the volume 2 that is associated to second container. And there is oil inside of the both containers, and it's having the flexibility of bulk modulus as it is shown here. The flexibility of oil is same here and here, no difference whatsoever. Okay, so how is that I can count the total volume of the system? Well, of course, that's going to be simple. I'm going to just add the volume 1 and volume 2 together. That's it. That's, by the way, same than the container sizes. So this is a volume of oil, this all in a container 1, volume of oil in a container 2, and this is actual container size 1 and 2. No difference whatsoever. And then I'm going to introduce the volume change. So what will happen then? Well, again, remember what happens. You know, the oil will get smaller, it will be compressed. In the first volume and in the second volume, it will be compressed. What's going to happen to containers? They become bigger because, you know, that's what the flexibility of how it will affect. So that's container 1, container 2. And then simply going to go ahead and use the definition of bulk modulus that is defined here. I substituted that to that equation that I got from the previous slide, and now I can get this kind of definition that I have here, effective bulk modulus, and then I have here a total volume and the difference in the total volume. And the total volume is actually the one that is defined here. Now that's how it goes. Now, substituting all that information like is expressed here, I will get the definition of effective bulk modulus like it is shown here. So that's what I'm after. That's the component that I really wanted to define. Right, so let's take all the other matters here from the left-hand side of the equation and put it in the right-hand side of the equation. This is the definition of bulk modulus. Now, what affects the bulk modulus? Obviously, you know, the bulk, the flexibility of fluid itself affects, then the flexibility of the first container, first container, second container, they will affect, and that's the way that I can define the effective bulk modulus. Then some simplification here, I forget this, excuse me. So I'm saying that the total volume is going to be the volume 1 plus volume 2, and volume of the fluid itself is roughly same as the container. And using this definition, this is how it simplifies my definition of bulk modulus. Excuse me, effective bulk modulus. So that's really what I would like to solve here. So again, what are the components that are affecting it? So the flexibility of fluid, flexibility of the container 1, flexibility of the container 2. Simple like that. Now, the dissolved air is not yet accounted, but that's a component that I can add. In a similar procedure that was the flexibility of the container was added, so I can add that to this equation. So finally, my effective bulk modulus can be written as it is shown here. So now let me summarize here. I have flexibility of fluid, flexibility of the first container, second, and so forth. So many containers where the flow can travel without the pressure losses, and the flexibility of fluid. And each one of these flexible shores is associated to their size. That's how you can compute it. We will practice that a bit later, but that's roughly how it looks. Now here's a measurement. Here's an example how the dissolved air will actually affect the flexibility of fluid. I need to make this a bit bigger to read it more carefully. So I have here x-axis, that is a pressure, and it goes from 100 bars, so this is 100 bar to 200 bars. So those are realistic numbers you can find in a real life. And then this is a bulk modulus, And look at this. So this is a value. That's roughly the value that we said that is a flexibility of fluid. And now I have here different scenarios. I have here 0% of dissolved air, so it seems to make no difference whatsoever. Then I have here 2%, 5%, 10%, and 15%. 15% may be a little bit extreme case, and it seems that it's lowering the flexibility very significantly. And it seems to be quite important all the way to pressure that is, say, 150 bars. But the way we will account this in a simulation is that we're going to just say that there is a certain amount of, assumed amount of dissolved air, and that's going to lower the flexibility, and that's it. Here's a measurements that I took from the flexibility of hoses. Now this is a little hard to read. What I have here is external pressure, and then I have here effective bulk modulus. And this is how hose itself will introduce extra flexibility to the system. And you can see that depends on the hose type, but it's roughly a square root like it is shown here. And now if you look at the numbers here, the numbers are surprisingly low. So effective bulk modulus here, that's 320 megapascal. Remember, the original fluid flexibility was assumed to be 1,500 megapascal. So it's quite significantly lowered because of the hoses itself. So rubber hoses is actually something that is a significant amount of flexibility. How we're going to handle that in the real life, we will get back to that in a bit later, not this week, but next week, when I have my examples about the modeling. Now, this week simulation assignment is shown here, or is actually solved here. I'm expecting you to solve the natural frequency of the system, that is where the flexibility is actually introduced because of the hydraulics. You know that the natural frequency, there are two major components you need to compute it. So you need to know the flexibility, and you need to know the mass. And it's all about the relation between the flexibility and the mass. The natural frequency you can take by taking a square root of that relation. Okay, so if I have a setup that is shown here, which is a mass here that is lifted by hydraulic cylinder, and the question is that what is the natural frequency of this system? How is it we can compute that? Well, we can compute it, but because we know that we know that the flexibility is all about the difference between the force and displacement. And now, with using that information and with using the definition of bulk modulus, is it still all right? Okay, so once using this relation and once using the definition of bulk modulus, I'm actually able to solve this problem. So let me show you how it goes, because this is going to be very useful to you when you're solving this weekly assignment. Okay, so here, how is that the force difference, which is used here, how that can be defined? How the force produced by the hydraulic, how that can change? You know that the force produced by hydraulic cylinder, it will be pressure multiplied by a corresponding cross-section area, right? So force produced if you have this kind of simple cylinder, and then there is a pressure applying to this end of the cylinder, how much the force is actually produced to this direction, that will be that pressure multiplied by corresponding cross-section area, which is this one here. Clear? How the force can change its values? Well, it can change its values only if the pressure changes values, because the cross-section is not the variable here. It is a dimension that is not going to change no matter what you're going to do to your, that if you're going to make another cylinder, then it's going to be changed. But if you have one single cylinder, it's not the variable. So I have here pressure that is applying this side of the piston, like shown here. And then I have another side of the piston that is applying here. The opposite in a direction, so that's why here I have minus sign. So here is a pressure and the force applying here, and the pressure and the force applying here. Now, the difference in this x direction, that would be all about how is a volume change associated to this one and a volume change associated to this one. Now, using this information, you can define your stiffness as it is shown here. And now, if I'm going to use the definition of bulk modulus, I can express my stiffness like it is explained here. That's exactly the equation you need in order to solve this weekly assignment. How it sounds. Again, I know that is 1 o'clock, but let me ask you this, and then we have a break. My question is, bulk modulus in a hydraulic describes force produced by cylinder. This is what is a physical interpretation of bulk modulus. Then the flexibility, compressibility of hydraulics, oil amount in the circuit, number of components in a hydraulic circuit. So 4 options, only one is correct. So it should be visible now. Can you see it? So let me take it back here. Okay, so let me see how many students we have today. What is that? Are they? So let me go here. So they say friction in cylinder. That's not the option here. Okay, so here's my hint. Oil amount at friction is not the correct answer. So option number C is off the picture. Number of components. So C is not, for sure, is not going to be the correct answer. So listen to me. C is not a correct answer. So it left 3 options where you can select the correct one. Now think about what we've been discussing. Have we discussed about the number of components? So we have discussed about 2 matters, but only one is correct. Okay, so let me take a look at, so we have 61 students. You guys all done? You all? You entered your answer? Okay. So it seems that the 2 students are still thinking, no, okay, now it is. So this is it. Is this a moment of truth? I think that it is. I'm kind of sensing, I have very positive vibe. Very positive vibe. Do you? No? No? Okay, 95 is a record high, isn't it? 97, was there really 97 once? This is still very good, because you have to consider that we have 62 students. And now I think like, okay, maybe two of them voted this force produced by cylinder. So we discussed how is a force. A force is about pressure multiplied by corresponding cross-section area. That's how hydraulics produce the forces. Number of components, we haven't mentioned anything about components, so it's going to be later in the class, not this time. The correct answer is the flexibility. It's all about the flexibility of hydraulics. But you got it all.
But they were listening this time.
But I'm kind of consider myself as a successful teacher. What do you say?
Yes, because they didn't, I didn't write friction on the
Yeah. So it wasn't you that is voting the A or D. Someone else. Okay. So this is it. So I know that it's already a bit late to have a break. Let's have a break for, what do you say? Can we have a break of, say, 10 minutes and then we continue? And let me promise this to you. This time I'm going to make a promise, and I will make sure that we're going to close 5 to 2, because it's 1 o'clock. So 5 to 2. So we're going to have a 10 minutes break, and then we're going to close 5 minutes early. Deal? Okay. So let me close the recording and streaming.